Hi, this video is called Function Families. It is the second video in this transition day in chapter 3. The first video actually is when we talked about function families. This one is more about transformations, but it is also super important information to help the second half of chapter 3 go well for you. So take some good notes and here we go. There's transformations. There's lots of different ways you can take an object and change it. We're going to focus on these four of translations, dilations, reflections, and rotations. Some of you visually are going to be able to do this super easily and have no problem with it. Others of you, visually it'll be a little bit more difficult, so you might rely a little bit more on some rules I'll give you. So just a quick review. A translation is when you take a shape and maybe we're going to move it to the right and up. So my original shape starts here, and then after I've translated it to the right and up, it will end up there. So that's a translation. The right and up, it looks more like a diagonal one. It's a slide. Sometimes we think of translations as slides. Dilation might be my favorite. I think it's kind of fun. When you dilate something, you take it and it has a scale factor. It either grows or shrinks by the same amount. Now notice the dilation, the shape of the house or the arrow or whatever you see there has not changed at all. That part is the same. It's just the size is different. It's almost like it was a balloon that got blown up. A reflection, think a mirror. Think of a mirror. If you had a reflection along this green line right here, if this was a piece of paper and you folded, and maybe this was all paint, this one on the left was all painted and you folded it up, this guy would meet up with this guy. It almost like creates a stamp. This guy would meet up with this guy. It's important to remember also that reflections don't have to be from left to right. They could also be what we would call a vertical reflection, where here maybe the line of reflection, the piece of paper is getting folded on the blue line. This guy would line up with there. This guy would line up with there. We're going to talk about different kinds of reflections. And then finally, rotations, super fun, is you take your shape. If we're going to rotate it, let's say 90 degrees clockwise, it would end there. Or if we started up here, if we rotated 180 degrees clockwise, it would end there. Rotations can be clockwise, going to the right, or counterclockwise, going to the left. Maybe we do 270 degrees counterclockwise, would end us here. So those are the different rotations we're going to talk about. And if visually you struggle with that, here I'm going to give you some rules to help it go just a little bit easier. All right, so let's start with our translation. A translation is that slide again. The keys to this are simply to pick important points and make a rule. So when I look at this picture, this would be worth copying down. We have an original function. Looks like a line with a little U shape and then a horizontal line. It gets translated up to this guy in red. Notice it looks the same. It hasn't stretched or shrinked or rotated, but this point on the bottom left-hand corner ended up still in quadrant 2, but it ended up to the right and up. So if I was gonna, and let's maybe check one more important point, this little guy right here ended up here. It also went to the right and up. And a translation, it should change the same amount. It looks like to get from the original point to the new point, it was 1 to the right and 2 up. Now keep in mind, when you move to the right or left, that's changing the x value, and up and down, that's dealing with the y value. So to write a rule for this, you take any point x comma y, and to move it 1 to the right, you'll take whatever the x value is and add 1. And then to move up 2, you'll take whatever the y value is and moved up 2. So that would be, if it ever said to write the rule, that would be how you would write a translation rule, where how far left to right it goes gets marked with the x, how far up or down it goes gets marked with the y. Let's just check a couple. This first important point was -2, 0. If we just plug it into the rule, x plus 1, that's -2 plus 1, and y plus 2, that's 0 plus 2, that's going to end up being -1, 2. Well, is that where -1, 2? That sure is where it ended up. Let's try one more with, what was the second one? It was 3, 3. If you write the rule, x plus 1 would be 3 plus 1, and y plus 2 would be 3 plus 2. It should have translated to the point 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, 5, which is right there. So I believe that rule is correct. So you can always do that with translation. Kind of think of how you would say it, 1 to the right and 2 up. That'll figure how you can write the rule, and it would help you with all your new points to translate something. All right, reflections, to keep going, reflections. If you have something that reflects over the y-axis, well, if this is our little grid, here's our x-axis, here's our y. So reflection over the y-axis, we also consider that a horizontal reflection. Because it's going, the reflection's happening from left to right. This point would match up with this guy. This one would match up with here. You fold on, it's like you fold a piece of paper on that line of reflection. Now think about it. This x here on the left would have a negative x value and a positive y value. Its reflection on the right, well, it looks like the x value changed from negative to positive, but the y value stayed the same. So when you have a reflection over the y-axis, or a horizontal reflection, it's the x value that changes. So the official rule would be you would take any point on the original, x comma y, and you would do the opposite x value, and then the y value doesn't change. So this negative means the opposite of. So that is the rule for reflection over the y-axis. All right, let's see what's going to happen if you have a reflection over the x-axis. So that's going to look a little different. Let's set this up a little bit better. A reflection over the x-axis, well, if you kind of sketch in your graph, the x-axis is here, y-axis is here, so we would call that guy a vertical reflection. Because it's reflecting up and down, where this guy would match up here, maybe this guy would match up with that guy right there. So what happens is if you look at the original guy I had marked with an x, it looks like the x value is positive and the y value is positive. But if you would think of the ordered pair of this guy down here, the x value will still be positive and the y value will be negative. So when you have a vertical reflection or a reflection across the x-axis, it's the y value that changes. So to write a general rule is you take any point on your original image, and to get its corresponding point on the reflected image, you'd keep your x value and you would take the opposite of your y value. All right, this next one, reflecting over the line y equals x, is kind of tricky to think about. We're going to do our best. It is also known as, if they say reflect over the line y equals x, it also might be worded as reflecting across the origin. And what ends up happening here is both the x and the y change. And I'm jumping a little bit ahead. Let me give you a picture of that. If you started, make these a little smaller, what would happen is if your original started in quadrant 1, its reflection across the origin, or its reflection over the line y equals x, would look like that. You could think of it as if there was kind of a spinner from the origin going here, it would spin 180 degrees, and that's where it would land. So when you write the rule, you take any point on the original, and if both the x and the y change, you do the opposite of both of them. So for example, if your original was a 5, negative 3, your reflected image would be a negative 5, positive 3. All right, and then the last one were for reflection. This is a long slide, the reflection one. I recognize that. I'm going to use a little bit of a different picture. We saw this in our translation picture, where we have an important point at negative 2, 0, goes up, you've got this U, and then it goes straight across. When it talks about reflecting over a line, in this case it says y equals 1. Maybe sometimes it would say y equals 4, y equals negative 1. In this example, y equals 1 is a horizontal line right here. Now for this kind of idea, reflecting over a line that's not the x or y axis, you're really not going to have a hard and fast rule. You kind of have to do this by hand and pick some important points. I'm going to pick negative 2, 0. I'm going to pick 3, 3, and how about 1, 3. And what we have to do to reflect across the line y equals 1, think of that line as a piece of paper again, and that the red guy, the red function has like marker on it. You fold the paper, what would you get? This guy right here, since it's 1 away from the line of reflection, you have to go 1 the opposite direction. It will land there, and that will land at negative 2, 2. All right, this guy, well, we have to go down 2 to get to the line of reflection, so I'll go down 2 more, and that's going to end up at 1, negative 1. So there's not, oh, no, that was this one, sorry. So there's not a hard and fast rule here. I think visually is the way to go. For this important point, we go 2 to the line of reflection, so we go 2 more. And then this guy, we went 2 to the line of reflection, so we go 2 more. And then I think it's not too bad to say, okay, well, this would look like this. There's that U shape straight across. If you needed 1 more point, this guy right here is 1 away from the line reflection, you go 1 more. So then you can see what your new picture would look like. All right, those are the rules for reflection. We're getting closer. Dilation, pretty easy. If you're going to dilate something, it's going to have a scale factor. The scale factor tells us how much our shape is going to grow or shrink. Scale factor, for some weird reason, they use a lowercase k to stand for scale factor. If a k is bigger than 1, the shape is going to grow. It's going to get bigger. If k is between 0 but less than 1, it's going to shrink. So in this example, when we have a dilated shape by a scale factor of 2, the rule is easy. It's you multiply, or you double your x value and you double your y value. So like looking here, if you had to draw this star again, and those don't exactly match up, so it's not a great example, but if you had to draw it, you'd pick some important points. Like I see this point right here, if I had to guess, I'd say it's at 1, 2, 3, 4, 1/2. So if that's the original point, what you would do to figure out where it goes to get bigger is you would do 2 times your x value and 2 times the y value, and so it's going to end up at 8, 1. And then you would do that for different important points around the star to figure out where it would go, to how it would get bigger. We'll practice a lot more than that, okay? Then lastly, rotations. Rotations, if you are rotating something 90 degrees clockwise, let's say you had, I don't know, a person here to go, and then I'm going to move him him so his foot is on the origin. It's just a better visual, I think. To go 90 degrees clockwise, he's gonna end up in quadrant 4 because you've moved 90 degrees clockwise. It'd be important to remember that 90 degrees clockwise would be considered 270 degrees counterclockwise. So 90 degrees clockwise and 270 counterclockwise will end you at the same spot. The rule you will use here is if you take any point on your original image, what you have to do to get your new image, it's kind of interesting, is you do the opposite of y, comma, x. So an example for that, if we started with a point -2, 7, well, the opposite of y would be a -7, and then the original x would be a -2, is where it would go. All right, for a 90-degree counterclockwise, well, pretty similar. It could go 90 degrees counterclockwise, that would be the same as 270 degrees clockwise. If I was gonna do my little sketch of the person, I think you get it, maybe not. Clockwise, to go, what would that guy look like? It would be right here. It would be right there, 90 degrees counterclockwise. So then the rule you get is any point you would do y, and then the opposite of x would put it in a different position. So for an example, let's just stick with that point -2, 7. Well, the y is a 7, and then the opposite of x, it would become a +2. All right. And then lastly, 180 degrees. Sorry, I got distracted there, Miss Wagner. Maybe some of you know her from geometry. Was just knocking on the window and waving. I got distracted, sorry. 180 degrees, it's just that way or that way. So counterclockwise and clockwise doesn't really matter. If you're gonna draw the little picture, it's actually gonna look, of the little guy, it's gonna maybe look familiar to you, is that it's gonna end up right there, which is the same thing as when you were reflecting over y equals x, or sometimes people will call that around the origin. So the idea of reflecting over y equals x or reflecting about the origin or 180-degree rotation are the same. So the rule would be the same. Maybe you recall in that reflection, it's the opposite of x, opposite of y. So as an example, if we stuck with that original point of -2, 7, to do an 180-degree rotation, the opposite of x would make it a +2, and then the opposite of y, it would land at a -7. I personally think the rules for rotations are the most helpful because I think visually they are the hardest to do. But that's my opinion. You might find rotations visually super easy to see. And maybe you find one of the other ones a little bit more difficult. That's up to you. But that's it for the video. I hope this will help you be successful for the rest of Chapter 3. It sure will set you up for success. Thanks so much.